Training today's AI is a monumental task. It's expensive, power-hungry, and incredibly slow. Training today's AI is a monumental task. It's expensive, power-hungry, and incredibly slow. Training today's AI is a monumental task. It's expensive, power-hungry, and incredibly slow. We're talking massive data centers and eye-watering energy bills that create a huge barrier for developers everywhere. Traditional methods try to shrink models after they're built, but by then, you've already paid the full price. But what if AI could get smarter by getting smaller, while it's still in the middle of learning? Researchers from MIT have unlocked a total game changer, a technique called Compre-SSM. It intelligently identifies and removes dead weight during the training process itself, not as an afterthought. The results are striking: a 4-fold speed-up in training and a 90% reduction in model size. This is the beginning of a new era for sustainable, accessible, and ultra-efficient artificial intelligence. The era of lean AI is here. Let's dive into the details for the topic.
All right, today we are diving into a really cool breakthrough. It's all about making AI models smaller and faster. But here's the kicker. It does this not after they're built, but while they're still in the middle of learning. And that right there is a total game changer for how we build powerful AI.
So let's just start with this big idea. What if an AI could actually get smarter by getting smaller? Now, I know that sounds like a complete paradox, right? But believe me, it gets right to the very core of one of the biggest challenges in the entire field of AI today.
And that challenge? Well, you could call it AI's very, very expensive habit. Because, look, to really get why this new technique is such a big deal, you first have to understand just how massive and costly it is to train the AI models that we all use every single day. You know, building a really powerful AI model, it is a monumental task. We're not just talking about some clever code here. It takes a staggering amount of computational power. And that power, well, it translates directly into eye-watering energy bills. And of course, a ton of money. This creates this huge barrier to entry for so many researchers and developers out there.
So for a long time, this has left researchers stuck between a rock and a hard place. Really, it's this classic trade-off. Option 1, you train a gigantic, super powerful model, and then you try to shrink it down afterward. The catch? You've already paid that full, massive training cost. So then there's option 2, just train a small model right from the get-go. But the downside there is you just have to accept that it's not going to be nearly as smart or as capable. So naturally, to try and get around this whole dilemma, developers have come up with a couple of compression tricks. But as you're about to see, these old methods, well, they have some pretty major flaws. Okay, so these old methods really fall into 2 main camps, and honestly, neither is very efficient. First up, you've got pruning. Now think of it like this. It's like training an entire orchestra, getting them all performance ready, and then telling half the musicians to go home. You still had to pay to train everybody. Then there's knowledge distillation, which, believe it or not, is even more work. Here, you train a huge teacher model first, and then you use that model to teach a smaller student model. You're literally doing all the hard work twice. It's just not the best way to do things. But what if there was a completely different approach, a smarter way? Well, that's exactly what we have now. Researchers from MIT and a few other top-tier institutions have come up with a new technique that just completely sidesteps all of these problems. It's called Compress-SM, and its genius really is so simple but so powerful. It compresses the AI model while it's training, not after. So instead of waiting until everything's done, it intelligently identifies which parts of the model are basically dead weight, the parts that aren't really contributing, and it just gets rid of them early on. This allows the model to keep learning, but in a much leaner, much more efficient state. And this quote from Daniela Russ, who's the director of MIT's CSAIL, just nails it. She said, "It turns compression from an afterthought into part of the learning process itself." I mean, that's the whole shift right there. Compression isn't some cleanup job you do at the end anymore. It's woven right into the fabric of how the model learns and grows, right from the start. Okay, so you're probably wondering, how does this thing actually work? How does it know what to cut? Well, the secret lies in this really fascinating discovery about what happens in just the first tiny fraction of the training process. So the whole process is basically split into 2 phases. As you can see here, there's this short warm-up phase that's just the first 10% of training. During that time, the model is just learning like normal, but the system is watching. It's figuring out which components are the most important. And then, for the other 90% of the training, it's already running as a smaller, faster, leaner machine.
Let's break it down step by step. First, you've got that initial 10% warm-up training. Then, step 2, the system uses some pretty clever math to rank all the internal parts of the model, basically figuring out which ones are doing the heavy lifting. Step 3 is the big one. It surgically removes the parts that aren't pulling their weight. All that dead weight is just discarded. And finally, training kicks back in, but now with a much smaller, way more efficient model that, and this is the crucial part, still has all the important know-how it picked up in that initial phase.
Okay, that's the theory. It all sounds great on paper, right? But the real question is, does it actually work in practice? And the answer is a huge, resounding yes. The results they got weren't just promising, they were honestly pretty striking.
Just take a look at these numbers. The performance game is crystal clear. On a standard image recognition test, the model that was compressed using this new method scored almost 86% accuracy. Now, compare that to a model that was just trained to be small from the very beginning. It only hit about 82%. So think about that. You're getting the performance of a much bigger model, but with the footprint of a small one. It's the best of both worlds.
And if you think that's good, the speed gains are even more dramatic. We're talking about a fourfold. That's 4 times training speed up. When they applied this to the Mamba architecture, which is a really popular and powerful type of AI model right now, they were able to shrink its core components by almost 90%, and it still performed competitively. I mean, that is just a massive, massive boost in efficiency. All right, so let's zoom out for a second and think about the big picture. What does all of this actually mean for the future of AI? Because this isn't just some neat trick for a research paper. No, this has huge real-world implications for how we're all going to build and use this technology going forward. Really, the impact boils down to 3 huge things. First, we're talking about more sustainable AI. This drastically cuts down on the energy and resources needed, which is a big deal for the planet. Second, it's about faster innovation. Think about it. If an experiment that used to take you a month now only takes a week, you can test way more ideas way faster. And finally, and maybe most importantly, this makes powerful AI more accessible to everyone. It lowers that massive cost barrier, which means more people, more universities, and more smaller companies can actually get in the game and contribute. So what we have here is a really powerful solution for making AI training leaner, smarter, and just plain better. It tackles one of the biggest bottlenecks we've had for years. And that leaves us with one final question to chew on. Now that we've found a much more efficient way to train our models, what's the next great bottleneck we need to solve in the world of AI?